This is a release of binding energy, a worked example involving replacing turbine power with a fictional nuclear source. This is a review for a AP Physics 2 problem-solving test. Sulzer Brothers, a Swiss company, made powerful diesel engines for the container ships built for American President lines. The power of each 12-cylinder engine is about 42 megawatts. Suppose the turbines use the formation of 14,7 nitrogen for the energy-releasing process. What mass of nitrogen would have to be formed to provide enough energy for 24 hours of continuous work? Assume the turbines are 100% efficient. So we need a little bit of additional information, which is provided now. And basically, we're looking at the mass of the formed nitrogen 14,7 atom minus the masses of its constituent parts that are unformed. So 7 protons are the mass of hydrogens and 7 neutrons that are unformed. And we get this difference in mass of 0.112356. Nitrogen 7 is that much smaller. That means that extra mass has been converted to energy. Cool. And those are in AMUs, or U's, as we say in physics. So we have this difference in mass of 0.112356 U's. That mass has been converted to energy thanks to Einstein's non-relativistic E equals mc squared equation. Okay, so now we're going to go ahead and just plug in our numbers. We've got the 0.112356 U's, but I want it in electron volts, and I've got a conversion. It's 931.5 mega electron volts per c squared per U. And so I plug it into the equation, and the c squares cancel out, and we get the energy released is equal to 104.6596 mega electron volts. That's for each individual nitrogen 714 atom formed. Now we've got to go back and look at the power that we're trying to replace. We have 42 megawatts. Power is a watt is a joule per second, so that's 42 times 10 to the 6 joules per second that we have to replace with this reaction. So we're going to have to replace this for 24 hours, so we're going to have to do some dimensional analysis here. I'm going to start by converting the 24 hours to seconds. I've set up my dimensional analysis just because I like to do that, and I get a number of 86400 seconds. Taking a big look at it, with the energy for the turbines to work, it's 42 times 10 to the 6 joules every second. They're working for 86400 seconds. So the energy produced, the energy produced for each formation of 14,7 nitrogen is 104.6596 mega electron volts. The total energy we have to replace is 3.6288 times 10 to the 12th joules, but our energy produced is in mega electron volts. So we're going to have to convert one or the other. We're going to go to the mega electron volts and change that to joules. And from our handy-dandy AP Physics 2 equation sheet, we have 1 electron volt equals 1.6 times 10 to the negative 19th joules. Setting up our dimensional analysis and doing our numbers in the calculator, we get that we have per each formation of each atom 1.67455 times 10 to the negative 11th joules. And again, that's for each reaction. So how many reactions do we need to supply all the power? Well, this is again just really a dimensional analysis problem. So I set up the total number of joules that I need, and the joules per each reaction I put on joules on the bottom, and then I'll find out how many reactions I need to produce this much energy. And I get 2.167 times 10 to the 23rd reactions. But the original question was, how much mass do we really need of this nitrogen? So we have to form this many atoms, and how much mass is that? Well, we can go from U's to kilograms, so we can find out the mass in kilograms of an individual nitrogen atom of 14,7. So we get the mass of each atom is 2.3245 e to the negative 26 kilograms, and we need 2.167 times 10 to the 23rd atoms. So now we just do some more dimensional analysis, and we find the total number of kilograms. And we get 0.005 kilograms, which is basically 5 grams. End of problem. Thank you very much for your time.